Thank you for joining this session of Shadow the Scientist. My name is Shamika Marshall. I'm so pleased to be your host tonight.
Oh, nice. Okay. And I can definitely.
The Shadow the Scientist initiative is offered by a team at the University of California at Santa Cruz. Now, in this session, we have the privilege of shadowing members of the Gemini Observatory, the Gemini Observatory North team, including Brian Lameau and Denise Hung. The International Gemini Observatory consists of twin 8.1 meter optical infrared telescopes located on two of the best observing sites on the planet. The Gemini North telescope is located on Hawaii's Maunakea and is part of an international community of observatories. By incorporating technologies such as laser guide star adaptive optics and multi-object spectroscopy, astronomers in the Gemini partnership explore the universe in unprecedented depth and detail. Now, tonight's observations will take place behind me in the Hilo Base Facility control room. Okay, just a quick note. I am so excited to be here in the Hilo Base Facility where tonight's observations are taking place. As you can see the outside of the control room right behind me, and we have several people in the control room. And that includes 3 of our science hosts tonight, and we have several. So that's going to include Ekta Shah and Emily Peavy from the Gemini Observatory's Community Engagement and Education team. We're going to go over to Brian Lameau, who is in the observer's seat tonight, to get us started, and we can get an introduction from everyone. Brian, hello.
Aloha, Jamika. How are you doing?
Doing good. Happy to be here. How are you?
I am also very happy to be here. So yeah, I think as you mentioned, I'm right next door to you. You can see the Christmas tree right through the window over here. Jamika's on the other side of the Christmas tree. So for those who don't know me, I'm Brian Lameau. I'm a staff scientist here at Gemini North Observatory. I'm in one of 2 chairs that are helping to control the telescope this evening, if the telescope agrees with us. So it's myself in the observing chair, and I can go into what that means later, but I'm the person responsible for the science observations that will be taking place tonight. And then we have Denise Hung, and we don't have our main camera, but there's Denise over there. She's in our operator chair. And she's the important person here tonight. So she's the one in charge of the telescope, making sure that the telescope is safe and sound, and that it will be happy and healthy for years to come. And so she's monitoring all the systems, making sure that there's no precipitation or humidity, that none of our sensors are giving aberrant readings, this sort of thing. And so right now we're actually observing, we're on sky, and I am observer, so I will kind of go in between Shadow the Scientists and my observing duties. And we can share with you a little bit later some of the screens that we use for observing the actual observations themselves. But I'm gonna pass over to Ekta to maybe introduce herself.
Okay, hello everybody. I am Ekta Shah. I'm currently in India, as you can tell from the bright sunlight. I am a part of C3VO team. I will describe in a bit what that means. But I have been working on big structures of galaxies called galaxy protoclusters or protostructures. And we use these kind of big telescopes like Gemini, Keck, and Subaru telescopes to identify these kind of big structures. and I will tell you about them in a bit. And I just finished my postdoctoral research fellowship at University of California in Davis. And then I moved to India to do some outreach stuff and also potentially some research stuff. So happy to be here and welcome to the session.
Thank you so much, Ekta. And Emily, welcome.
Cautiously. There we go. Okay. Brian, do you want to turn off your volume? There we go. Okay, we're all in the same room as each other, so gotta be juggling the microphones and what speakers are on. Aloha, everybody. My name is Emily Peavy. I am the Senior Education Engagement Assistant here at Gemini Observatory, with a background both in astronomy and education. I'm happy to answer any questions that you guys might be having as they're coming in through the chat, so I'll be monitoring the chat. And as Jamika mentioned, we are based on the island of Hawaii. The Gemini Observatory is at the summit of the mountain Maunakea, which is the tallest mountain in the world, measuring it from its base to the summit area, so measuring from its base on the sea floor. And that is where our telescope is currently living and operating and moving around. However, we are a completely remote observatory, so all of the operations, all the science happens here at the sea level facility in Hilo. And we have our team behind me here, working in order to be driving the observatory. They're looking on going through the queue in order to see what objects might be interesting tonight and what science wants to happen tonight. We'll probably duck into a little bit of what exactly queue observing is, but it's just that everyone who wants to observe on Gemini Observatory will submit their proposals of what they want to be observing, when they want to be observing, and then our team here is going to be going through those proposals of what's actually going to be able to happen on sky tonight. And it's a really, really efficient process. Sometimes things will come up and actually interrupt that process though. I came in earlier today to get some work on and I walked past the control room and there's a big alarm going off saying target of opportunity, target of opportunity. Brian, do you want to talk about what a target of opportunity is?
Sure. Yeah, all good. Okay. You guys can hear us? Sorry, we're doing a lot of juggling in here. Our normal setup is on the fritz tonight.
You've been so super flexible and I'm grateful for it. Thank you. Thank you all. I appreciate it. But yes, we can hear you.
Cool. Yeah. So I came in to the same alarm. And what that alarm sounds like is exactly what Emily said. So it says, attention, target of opportunity. And this is one of the really amazing things about the Gemini Observatory. So I think Jamika mentioned in her opening remarks that we have a twin telescope in the south. So we can actually see the entire sky. I think we're the only observatory that can see the entire sky. And so I never really appreciated that, but yeah, that's pretty amazing. So there are scientists in the world that have a very strong interest in usually supernova events, so exploding, basically things that explode. And so this could be coalescing stellar remnants like white dwarfs. This could be an explosion of a dying star, some sort of event that happens very quickly on human timescales. It's not very often that happens in astronomy, but this is one of the few types of events that happen on human timescales. And so they have programs with us where at any time, if they see something from another telescope, there's usually dedicated smaller telescopes to keep an eye out. And they're monitoring, mostly the whole entire sky, or the whole entire sky over the course of several nights. And these scientists get these data, and there's some automated processing that occurs, and they see, you know, in their data, it's usually an algorithm that detects like an increase in brightness in a galaxy, for example. So you just keep taking a picture of a galaxy over and over, and then all of a sudden, for some reason, that galaxy gets brighter, and either that's an image artifact or one of Musk's satellites, or or there's something happening in that galaxy. And so if these scientists usually would confirm that before they would ask us to take a look. So they would confirm it on another telescope. If it looks like something's happened in that galaxy, they will send in what we call a trigger. So this is a request, but a very strong request, because we have an obligation. So they send a request, and it manifests as this alarm. And so when I walked into the observer room tonight, we had a plan from, you know, just looking at, well, not just, but looking at galaxies and things in the solar system. And, you know, we had everything nice and ready and our plan set. And all of a sudden we get this trigger. And that means we have to change plans at the very beginning of the night. And this is exciting because, you know, what we had planned on observing is not less exciting than this, but, you know, this is one of the wonderful things about Q observing, is that you think, okay, so how quickly do we need to go to this target? What's the request by the PI? What's the timing? If we move there very fast, is there some scientific advantage to that? And usually the scientific team will let us know that. They'll say, please sleuth there, move to that target within an hour or 2 hours, or it's okay to do one next week, no problem. And so then we honor that request. And so the one for tonight is going to be something we have to do tonight. So that's going to be something we're going to do later tonight. And we're actually going to make a move right now. So.
Thank you, Brian. So while Brian is
Can we salute
slewing,
40679, please?
we can go over to ACTA. ACTA, can you quickly talk to us about the differences between Q observing and classical observing, since you've used both as a science host in our Shadow the Scientist sessions?
Sure. So what happens is different observatories allow different level of participation from the people who propose the projects. So basically, the way the whole observing thing works is scientists from different places can apply for observations. So for example, I would propose that, hey, I think we should observe, you know, galaxies in the early universe, and then you have to make a case for that, right? Why you think that is interesting, why you think you can use this telescope to observe this kind of systems. So you have to provide like scientific justification about the systems, and then you also have to provide like technical justification that you can use this kind of telescope to get this kind of observations. And the time allocation committee of different telescopes, they go through this kind of proposals, and then they select you know, the best proposals. So if your project is selected, if your proposal is selected, then the question is like how much input are you gonna give while the observations are getting taken. So for example, if you are observing on Keck telescope, then the telescope operators are on the mountain, and they move the telescope itself. But as an observer, you get to control the instrument and you get to take the observations. Okay. So if my project is selected, I control the instrument and I can take observations myself. But for some other telescopes, for example, Subaru, if your proposal is selected, you can be present there while the observations are getting taken, but you don't get to control anything. Okay. And then there is a third thing, which is called Q observing, which is where I don't even get to be there while the observations are getting taken, but the people at the scientific observatories, like Brian, and Denise, they take observations and then they kind of send it to you. So they are kind of your, you know, your support staff that actually takes the observations. So yeah, I think, and another thing is also for many telescopes, they actually depending on what kind of observations you need, they have certain schemes. So even in Q observing, you have projects that go for highest priorities, and then projects that go for slightly lower priorities and lower priorities, and then depending on what kind of weather is needed for your project. So if the weather is best, then some projects will be selected, and the weather is not that great, then some other projects that will do fine for that kind of weather, they will be selected. So there are a lot of parameters. And then in this kind of process, if you know, this kind of certain thing can appear, then they have to change plans as well. So yeah, I think Brian is sharing the screen.
Thank you
Yeah,
for
thanks.
that explanation, Ekta. And yes,
I'll
Brian,
just
go
make
ahead.
one correction, Ekta, which is that you can be present while we take the observations. We're very happy to have company here, as you can see. We're very happy to have company. And in fact, tonight I was working. So if the conditions are good enough, I was working with a scientific team that I actually work with scientifically. And they requested eavesdropping. So we offer eavesdropping for any science team that wants to be present for their observations. And we have teams all over the world, so it's all different hours of the day and night. And we don't know, actually, because of the nature of Q observing, when we're going to be slewing to the target. So it could be that it's tonight, it could be that it's 3 weeks from now. It's hard to tell because we have to match the observations to the conditions. Okay, 200. Okay, thanks. Yeah, so I'm gonna acquire on our target. So this is just I can explain what happens afterwards, but I'm gonna go over to this screen, which is the screen you guys are watching, and we're gonna acquire our star that we're gonna be looking at.
Okay. So maybe I can give a little bit of context. So as you can see in the upper left part of the screen, we see a yellow dot. So that is what it looks like they're trying to acquire, right?
Yep, you got it, Ekta. Yep, that's what we're trying to. Yeah, this guy right.
And as you can see, they're kind of moving the telescope a little bit and trying out different focus values, I think. Is it focus or just kind of moving a little? Mid interval, plus and
26 minutes, please.
Exposure. So it's kind of like when you're, you know, taking a picture with your phone and you want something to be in center, but also in focus. So you have to try out different positions and different angles.
Yeah, so we're using so Gemini has a lot of different instruments, and usually for like classical observing, so Ekta mentioned the Subaru telescope or the Keck telescopes, they'll use, maybe on a crazy night, they'll use 3 instruments. Usually it's 1 instrument per night, sometimes 2 when they split the night. At Gemini, we're not particular, so we'll use any instrument, anything that's good for the science, because we observe all different types of scientific programs on a given night. The classical model is very different. As Ekta said, you show up as a program team, and you're at the telescope, and you're basically renting the telescope for the night. So you're renting it with the currency of your scientific ideas, and you've shown up and you said, okay, this is what I want to observe. And for stuff like myself, Denise, and Ekta all work on this project called Charting Cluster Construction with Woods and or else. It's a nested acronym. We love acronyms as astronomers. So I'm not going to keep going through the the Matryoshka of acronyms here, but it's looking at very, very faint galaxies in the distant universe. And so if we show up to the telescope, we're like, hey guys, we got a big telescope tonight. I drive up to Waimea, which is in the north center part of this island, about an hour and 15 minutes away. And I have time on the telescope. So driving up there and not having time on the telescope. I mean, it's nice up in Waimea, but so I drive up there, I have time on the telescope, and great, okay, one of the biggest telescopes in the world. Yay, we can see distant galaxies. Oh, it's cloudy. There's Sirius up in the sky. Well, that's not good. So if there are clouds, that attenuates photons from the distant universe, and it's very hard to see what we want to see. But we persevere, we attempt, we do our best to see to get the data that we want. But it's a challenge. Conversely, at Gemini, if clouds come in and we're observing a program that's looking for distant galaxies, probably not the best conditions for that particular program. So we pivot, and we move to a program that could accept a little bit more cloudy skies, maybe a brighter set of targets, or just it's not as demanding in terms of needing a perfect sky. And so that's actually the variant that we're in now. We call these different weather conditions variants. And we have absolutely beautiful skies right now. But unfortunately, the turbulence is quite high, either both on the ground and in the atmosphere. And so it's smearing out the starlight quite a bit. And so we're actually observing a fairly bright object right now. But this is probably near naked eye object, honestly. But we're using this MAROON-X high precision spectrograph. This is a instrument that disperses the light up into a rainbow, and it makes very fine gradations in terms of the rainbow. So it's not like red versus blue, but it's like red versus slightly, slightly more red, or slightly more towards the infrared. And so we can break up the light into very tiny packets, and we can measure the colors very precisely of a star. It's usually stars. But the downside of that is that you have to have fairly bright objects. So if you have very bright objects that have enough, that are giving enough light, if you're breaking that into 80,000 buckets, which is basically what you're doing, instead of one big bucket, when you take like an image, which is what you see here on the left. So this is just an image, and then we're porting the light through this aperture right here, this circle. That's what's called the science fiber of MAROON-X. This actually it's attached to our telescope. And this fiber is just a wire that goes down to the basement of the telescope and is attached to this MAROON-X instrument. So it's like almost like a light hose. It is a light hose. And so it goes down to the basement, and then it goes through this instrument that disperses the light, creates the rainbow, and then sits on the detector. And so what Ekta was describing is right now we're trying to take, or we are taking pictures every 0.15 seconds. So you can see this blinking right here. Every 0.15 seconds, we take an image, and we want to make sure that the light fits as best as possible into the science fiber, because we did all this work to, get the telescope up and running, to have all our software running. We have this absolutely amazing site to observe from. We want to get all the possible light that we can into the instrument. And so this is what this software over here is doing. And we're just watching the star in real time shift a little bit because of the atmosphere and the jitter of the telescope. It's actually windy too, so it could be the secondary mirror is shaking a little bit. And so we're making, there's this thing right here. It's called a tip tilt mirror measurement. So there's basically like a mirror inside of this MAROON-X instrument, and it's making slight movements like this to reflect the light right into the science fiber. So it's basically compensating for all this other movement. And then this down here is the spectra that we're getting out. And we're taking,
Well, real quick, is any of the data that we're taking right now relating to the target of opportunity we got later? earlier, we had a question regarding that target of opportunity and whether or not we would be able to learn the results of it over the course of the live stream.
So this one, no, actually, so the beginning of the night, we're taking MAROON-X observations. That was the plan. So we not only do we have to consider the conditions, but we have to consider what's up in the sky right now. And so I think the program team for that target of opportunity would be very, very excited if we could go there right now, because that's what they want. But it's not up in the sky, so universe not cooperating. Gotta find a different planet to observe from. And so we are going to wait until about 5:30 in the morning.
Oh, okay.
Hawaii time. Yeah, so
In order to be just looking at the target of
in order
opportunity,
to
to just start
yeah,
looking
so
at
it
it.
rises up in the sky
What section of the sky is it in?
roughly.
5:30 in the morning, so what's up around then these days? Sorry, you're doing multiple drops there.
Yeah, I'm gonna stop sharing for just a second so I
Yeah.
can check that.
Yeah, so yeah, target of opportunities are super, super exciting. The alarm does make it sound like you need to drop whatever you're doing and race over to what you need to take. However, we get that alarm even if the thing is not in the sky right now. I first heard the alarm when I was walking by earlier today at like 2 p.m. and I was like, I don't think we could see anything. We're an optical telescope. We're not seeing anything, so I don't think I need to worry about this right now.
Yeah, so that's it. It's 10 hours right ascension. So it's
I should know that.
roughly where like Cetus is, I guess.
Okay, Cetus. So that's kind of like southern sky.
Yeah, it's a little bit higher declination than Cetus, but yeah,
Okay.
it's in that
Okay,
in
yeah.
that neighborhood.
Yeah, one of the advantages of observatories in Hawaii is Hawaii is just around 20 degrees north latitude. So that means we do see 100% of the northern hemisphere sky and 80% of the southern hemisphere sky over the course of an entire year. In that section of the sky, were you postulating that this target of opportunity is likely supernova in another galaxy?
Could be, yeah. It may either be that or potential gravitational wave event.
Oh, that's exciting.
Yeah, so it's yeah, this is a very high priority observation. We're gonna get on there as soon as possible. And without giving away any details, it's likely something pretty exciting.
Part of the question was, if we're going to learn about it in live stream today, could we possibly learn about it a little bit later on? The answer is unfortunately no. We also even need to be careful with what information we're saying about it, since data collections can be a little bit proprietary sometimes about who gets the discovery first.
But I did get permission from another program team lead. So let me go back to sharing this. To talk about, so we're actually going to move to another target of opportunity. So it's going to be an exciting night tonight. In about 10 minutes, if all goes well, we're going to be moving to another target of opportunity, and this is a type 1A supernova.
Cool.
And this is a program that David Jones at the University of Hawaii Hilo has been running for quite some time. He's a former Gemini staff member. He's a good friend of mine, and I have the misfortune or fortune of supporting him on all of these programs. So I know his programs pretty well. My science is not supernovae, but he spends a lot of time looking at them, and I spend a lot of time looking at fixing his observations so that he can get good data. And so he is of this category of science that he says, hey guys, I'd like you to take a look, Gemini. I have a program, so I'm serious about this. I'd like you to take a look at some supernova that have gone off maybe a month ago. And so we already know about them, they're there, but we're just gonna kind of monitor them over time. And we're gonna see how things change as they evolve. So as the shell of matter that's expelled from the stellar remnant, how that evolves over time.
And type 1As are especially interesting
Mhm.
as well. So most people, when they think supernova, they think type 2 supernova, and that is large star coming to the end of its life and exploding out. Type 1A supernovae are a little bit different. They're still very, very interesting and very bright. But a type 1A supernova typically results from a very, very small star, the remnant of a star, that is essentially stealing gas from another star that is orbiting around, that they're orbiting around each other. So you get a big red giant star, and some of that gas from that red giant star is getting siphoned to the smaller white dwarf star. And eventually, if there's a bit too much mass on that white dwarf star from it stealing matter, the star will detonate and it'll explode. A really, really cool thing about type 1 supernova, type 1A supernova, is that they have a very consistent brightness. And the nice thing about a very consistent brightness is it allows you to get a very, very good measure of a distance to an object, because the distances in astronomy end up being one of the hardest things in order to figure out. Because a faint light bulb that's close to you can look really similar to a bright light bulb that's very far away. But if you know the wattage of the light bulb, if you know how much light that light bulb is putting out, then you can calculate distance to it. So a type 1A supernova is always the same brightness. If we see a type 1A supernova, we know exactly how bright it is, and then we can get a very accurate distance to the galaxy where it's occurring in. In the chat, we had mentioned that I got super excited over gravitational waves, and I can go into an explanation of what that is. That gives Brian some time in order to be doing his job.
Excellent. And then I have a question after that from the chat also. Go ahead.
Oh, wonderful. Yeah. So a gravitational wave event. So gravitational waves were something that were predicted over 100 years ago, coming into the scene along with Einstein's relativity. And the idea behind them is that we have the fabric of space-time. And if you imagine the fabric of space-time, if we collapse it down to 2 dimensions, imagine you have a bed sheet that you've stretched out while you're making your bed, and that's the fabric of space-time. Then you drop a bowling ball into that bed sheet. That represents anything that has mass, anything that is made up out of matter. And when you drop that bowling ball into it, it'll create a gravitational well going down. And that's the basics of how gravity works. What a gravitational wave is imagine that while that bed sheet is getting stretched out and that bowling ball is sitting in the middle of the bed sheet, someone pushes the bowling ball and causes the bowling ball to move. And when that would happen, the bed sheet would ripple, going off in different directions. And that's what gravitational waves are. It's something in the universe that has mass and is moving will create gravitational waves. And so right now I'm making gravitational waves. I talk with my hands a lot, and as my hands are moving around, they're making little mini gravitational waves going off in all different directions. The gravitational waves I'm making with my body are pretty small, because I'm a pretty small thing in comparison to the rest of the universe. So the biggest, strongest gravitational waves are things that are very, very big and are moving very, very fast. But why is this such a big deal? Well, gravitational waves were theoretical. Like I said, they came onto the scene with Einstein's relativity. We did not detect any gravitational waves until 2015 was the very first detection of gravitational waves, and that was detected through the Hilo Observatory in Washington, which is a gravitational wave detector. Since 2015 to now, which is, oh wow, pushing a decade, a decade really soon actually. Wow. In this past decade, we have been getting more and more gravitational wave detections. And honestly, gravitational waves is what's going to rewrite astronomy science, because gravitational waves are not connected to any other way that we've been discovering things about the universe. Every other way that we've discovered something about the universe is through light. Gravitational waves aren't connected to light. So we now have finally something else that we can use to study the universe that is nothing like the ways that we've studied the universe before. So we're going to be completely rewriting much of our science with gravitational waves.
Yeah.
So But gravitational wave detector, why is it so exciting for us to come in and get target of opportunity of gravitational wave detection? Well, what that means is that LIGO, or another gravitational wave observatory, which we can't detect gravitational waves, we're only set up for optical light. And a gravitational wave detector somewhere else in the world has detected gravitational waves, and the way that those gravitational waves look indicate that it could be an event that is also producing light. And so that gravitational wave detector, usually LIGO, but a few other gravitational wave detectors are coming online. They send out the alert to all of the optical observatories. The optical observatories will then want to try to drop what they're doing and take a look at that thing that is creating gravitational waves. It might also create light. And by comparing that observation through all these different ways of detecting it, you get a lot more information about it, and you might even rewrite some science while you're doing it.
Thank you so much for that, Emily. Sorry. So I got a question about gravitational waves also from Richard. And Dustin, I have not forgotten your question, so we'll come back to it right after Richard's question on gravitational waves. But let me first say that I'm really excited to share here that I've had several meetings with staff at LIGO to have sessions, gravitational wave sessions with them, observing their work. Hopefully sometime in the early part of next year. So definitely keep checking out our website to find out when we have those first LIGO sessions. Okay, so the question from Richard, thank you all for your questions. The question is, and this is for Emily, Brian, Denise, Ekta, are gravitational waves what holds planets to suns and suns to galaxies? And I'm pretty sure that that's not the case. It's gravity, but maybe Ekta, could you give us a bit more detail on why it's gravity and not gravitational waves? Because it seems like there is maybe some bit of explanation needed to define the two things.
Yeah. Yeah, so like you just said, I also think that it's gravity itself, and the waves are generated when there is motion in the space-time fabric, right? So while the planets are moving around sun and they are creating their own gravitational waves, that's not what's holding things together. It's so when you have a very massive object and it creates this dip in space-time fabric, and the curvature of the space-time fabric itself changes, kind of like, you know, how Emily was saying that you have a bed sheet, and if you put bowling ball in it, so the curvature of your bed sheet will change. So it's that shape itself. That's why things move. That's why like galaxies are moving around. Sorry, not galaxies are not moving. That's why planets are moving around sun. And with that being said, I think Emily gave such an amazing explanation of gravitational waves. I just want to add one little thing to that, and which is why it took us so long to detect them. And that is because when gravitational waves are passing, you know, they are creating this ripples in space-time. But that change in space-time, it's like the space-time itself is changing length. And that length that you need to measure to detect waves, it's kind of like 10 to the minus 20, 10 to the minus 21 scale, okay? So which means that if you have like kilometers long,
I think she's getting a little stuck, but I'll add in on what she's saying is that you need extreme sensitivity in order to get this. So the LIGO detector, I once heard somebody from LIGO describe that the LIGO detector is so sensitive, it can detect a star the size of Arcturus moving the width of a human hair. That's how sensitive the LIGO detector is.
Yes.
Like, what, 10 times the size of the sun, something like that?
Something around that ballpark.
Yes. Oh, and I think we have Ekta back. Okay, Ekta, please continue. Emily supplemented what you were saying, and yes, okay, we'll just flow back to you.
Yeah, my Zoom could right at the moment, but I was just having small scales. But yeah, so it's only recently that we have that kind of technological capacity to measure that kind of change, and that itself is unbelievable achievement. Um, so yeah, I hope at least that answers the question that what's holding things together.
Yes.
So I'll just jump
Excellent.
in for a second. So I'm sharing a screen right now, which actually we rarely get to see on Shadow the Scientist for Gemini. This is our observing tool, and it's normally not shared because this is proprietary information that a proposing team gives us in confidence, and we do not share it unless we get the express permission from that team. This is the program that I was speaking about earlier. So this is David Jones's program. And this is the target of opportunity that we're going to salute to next. So we have just one more observation that we're currently taking. You can see this exposure remaining bar down at the bottom. So we're taking one more exposure. The exposure time is 300 seconds here. So about 150 more seconds, 2.5 minutes, and then we'll be moving to our next target. So we'll stop with the MAROON-X observation, and we'll move the telescope and we'll move to a different instrument. So this is what I was mentioning earlier. We use usually 3 to 4 instruments per night at Gemini. And so we have a tertiary mirror that goes into the beam of light that we collect from the sky, and it redirects the light into the different instruments that we have mounted down at the bottom of the telescope. And so actually I can share, I want to share the screen. This one here. Okay, so just to give everybody an idea, this is our telescope status display, or TSD. This is a 1980s pictorial representation of the Gemini North telescope. This is our dome here, a bird's eye view of the dome. This black rectangle is our shutter. This is what the big pieces of metal that basically keep everything but the light out. And this circle right here is a representation of the telescope looking up in this portion of the sky. And so the light comes down into the telescope here, bounces off the primary mirror, bounces to a secondary mirror, goes through an aperture in the middle of the primary mirror, and drops down into what we call the Cassegrain cage, or the instrument cage. So there's actually like a pipe, again, the light pipe that's sticking out of the primary mirror, and the light's moving in through there. And so in a second, once we go to the next observation, we're actually going to put in the tertiary mirror here. It's going to cut the light. So we have this light going to this visitor number 1 here. This is MAROON-X. So MAROON-X is an instrument that's run out of University of Chicago. It's going to become part of the Gemini North family of instruments officially, probably in the next couple of years. But we work very closely with the Chicago team. And so it's basically like a facility instrument right now. So don't worry about that visitor. It sits there pretty much all the time. But so the light's going to MAROON-X. We've just finished the observation. So I'm going to queue up the next observation, and then I'm going to ask Denise to move us there. And in fact, I already did that. So Denise, can you salute to 319-170, please?
So exciting that we get a chance to actually be a part of going to a target of opportunity. All right, so while things are in motion, Dustin, you've been so patiently waiting for the answer to your question. So let me share it with our science host here. So the question is, can you see anything during the day using filters? So Emily, Ekta, Brian, Denise?
Gemini telescope is designed for nighttime. You do not want to take it out during the daytime at all. The sunlight is way too bright, way too many photons, specifically for Gemini Observatory. As Brian was mentioning, he was going over like the different parts of the telescope that you can see in the diagram, and that primary mirror is 8 meters in diameter and one big light collecting bucket designed to be collecting the faintest bits of light from very, very far away. So it's a telescope it's an observatory that only wants to be used during night. However, there are many observatories that are designed in different ways in order to be observing during the daytime. There, in our family of observatories here in Hawaii, there's the Daniel K. Inouye Solar Telescope, or DKIST, on Maui, and that is a solar telescope that it is completely designed and functioned to look at the sun. And that's the only thing it does. It only looks at the sun in order to collect data from the sun. And it's not something that you could like redesign, look at the sun during the day, redesign it, and then look at stars at night. No, it's only designed for looking at the sun.
I need a different guide star. This one looks a bit long.
It's too faint.
Is it double?
It's double. Oh, sorry. Okay.
We're gonna switch what guide star we're focusing on. There's it ended up being a double star. So yeah. So anyway, other observatories such as radio or submillimeter observatories. So in our Maunakea observatory family, there is the submillimeter array. There's the James Clerk Maxwell telescope. There's the Very Long Baseline array. Those observatories, because they're just looking at a completely different section of the light spectrum, they don't need to worry about daytime or nighttime. But once again, they're observatories that are very different from ours. So our observatory got a nice big mirror that collects light and then bounces it to a secondary mirror to focus that light and then bounces it into our instruments. If you didn't know that a radio telescope or a submillimeter telescope was a telescope, you might think it's your satellite dish and connect to your TV channels, because it does look very, very similar. But the radio telescopes and submillimeter telescopes here in Hawaii, their advantage of being on Maunakea is more about moisture in the air and less about being above, well, being above the atmosphere helps with moisture a lot, but they could potentially be observing during daytime. I will say though that most observatories reserve daytime hours for maintenance, because if you need to be doing any maintenance on your observatory, you want to choose when the sun's up in the sky. The exceptions are though, like just like as at Gemini, while we have targeted opportunities, the James Clerk Maxwell telescope and the submillimeter array also do targeted opportunities. One of the projects that they work on is the Event Horizon telescope, where an array of radio telescopes work together to collect an image of a black hole. And they do want to have those observations be happening at the exact same time around the world. So sometimes observing during the day during that time.
Yeah, just to say that we're 7 hours difference from Chile right now. So also if something happens in our daytime and it's visible to both telescopes, it's possible to actually a program, if they ask for a trigger here, it's possible to send that to Gemini South, and Gemini South can actually observe it, depending on the instrument. So we have different instrumentation suites, but we have one instrument that's basically the same, roughly, in the north and the south, with a few tiny exceptions, and that's GMOS. That's our main optical imager and spectrograph. And a lot of the target opportunities either want an image, or they want a spectrum, or they want both. Actually, probably 2 weeks ago, we had somebody trigger on a target of opportunity. They said, I don't know where it is, but it's somewhere roughly in this part of the sky. We took the observer took an image, and then 3 hours later, they said, found it. I'm going to trigger again. And they asked for a spectrum, and that's, I mean, that's amazing. Like the back and forth, and I think SPI was in Japan too.
The guiding at 100 neutral.
100 neutral. Okay, thanks.
Do you remember what the subject of that TOO was?
I do.
Supernova.
Right? Are you allowed to say? Is it
As long as there's no follow-up questions.
Okay, yeah. We can't tell you where. You can't tell you how to find it, but it was a super.
It was not actually.
Oh, never mind.
It ended up being well, it could have been. I don't
Okay.
know.
You gotta, if you're gonna be mysterious, you need to give us what magazine to look at in order to find out later.
Let me get acquired on our target and then we can
Yeah,
talk.
sorry.
Let me just say that while we're acquiring on this next target, which I believe is going to be the target of opportunity, we've had join us in this session the founder of Shadow the Scientist, Raja Guharthakurta, who is currently just joined us. I believe, Raja, you are in India. Oh, but I can't hear you, Raja, and maybe you're not talking
hear
to us
me?
right now. Yes, now I can hear you. Yes, hello.
You can? Okay. I'm actually in Kolkata. I'm here with a group of teachers in this wonderful organization called ALTAIR, which means one star, right?
Yes.
But it's also a play on words because it's also name of a one-stringed instrument when those are put together. But I was just describing who the other members of the team are. I am indeed in Kolkata. It's 11:30 in the morning. So you guys, your session has been going for an hour, is it?
Yes, and we're actually going to be wrapping up here in about 5 or 10 minutes or so.
Okay.
We're shortening it, so you joined right at the right time.
Okay, I'm glad I caught you. We were just talking about Shadow the Scientist with a group of educators here who run this wonderful program for girls, a learning center for girls here in Kolkata. I'm going to be visiting Future Hope, Jamaica, in a few days. And I will be visiting Shanti Bhavan and Creative School next week. But Brian, I was singing your praises a moment ago, saying you've grown up from being an undergraduate to being a professional astronomer.
Oh, Raja, nice to see you, by the way.
Yes, Raja, and to all the guests there, I'm so glad to have you with us. So right now, Brian and Denise, Denise is operating the telescope for us, and Brian is in the observer's chair tonight. And so in the control room also you have Emily Peavy joining us from India is Ekta Shah, who has been a science host on Shadow the Scientist many times. So right now they were acquiring an image for a target of opportunity. And I see, Brian, it looks like we are looking at something interesting.
Yeah, so we just got our first two images. Let me walk through what this is. So this is the GNIRS spectrograph. This is one that I'm helped to be responsible for at the observatory. And this is our near infrared spectrograph. And what you can see right now is an image of our slit. So we have what's called a cross dispersed slit. And we're going to be trying to place the supernova. It should be that thing that's moving around between these two frames. So you can see there's a little thing moving around there and there. We're going to try to put the slit exactly on that blob of light there. So I'm going to have to concentrate for just 1 second.
I'm enthralled. So this is going back to the Type 1A supernova program that David Jones is based in here in Hawaii, who's going through. So this is the really bright explosion. Bright explosion that we know exactly how bright it is.
Yes, absolutely. And one of the things I meant to follow up on, Emily, is because you gave such a great explanation about it, and I did put it in the chat, but I didn't talk about it, was that because of the particular kind of light that's put out and we can know the distance, Type 1A supernovae are used as standard candles. And so maybe while we're waiting for Brian and Denise to kind of get settled on what they're doing right now, we can talk to us about that.
Yeah. So standard candle is kind of just what I was describing before, that the distances in outer space end up being the hardest thing for us to determine. And that's for truth for all of humanity's era of looking at the stars is it's really hard for us to determine how far away things are. And it was actually only a century ago when we really figured out that there were other galaxies. In the 1920s, there was this big debate in astronomy of, is everything just inside the Milky Way and the Milky Way is the whole universe, or are there other things out there that are like the Milky Way? And that was what was being talked about 100 years ago. So we've only really had this concept of just how big the universe is and how these little fuzzy things are super far away for not that long. And as I mentioned before, so how we determine distances we start by looking at things that are really close to us and getting really good understanding of how far something is from us. Like us to the moon, we'll get a really good accurate distance to that. Then us to the sun, thus to the other edge of the solar system. And we build what we call a cosmic distance ladder, where it's like you're building up the different methods of how to calculate a distance to an object. And we call it a ladder because you need to be really secure on one rung before you step up to the next method that is going to get you a little bit farther in outer space. One of the big things, though, that really did help with this getting an accuracy of how far things are, I mentioned in the 1920s, that was when there was this big debate over, are these fuzzy things in the skies that we now know as galaxies, are these fuzzy things close to us or are they very far away? And the way we determined that was through the work of one of my astronomical historical heroes, Henrietta Leavitt, and her research was studying Cepheid variable stars. And those are stars that will steadily get brighter and dimmer and brighter and dimmer. It's just that their atmospheres aren't quite balanced. But she figured out that as these little variable stars are getting brighter and dimmer, when they get bright, they're always, every single Cepheid variable star, it hits the exact same level of brightness, which is called luminosity when it's at this bright point. And so if you can find a Cepheid variable star in another galaxy, you know how bright that variable star is. And then there's a very simpler formula that relates brightness to distance. If you know exactly how bright something is, we calculate that distance. And that's how we first determined that the Andromeda galaxy was something that's not that close to us. It's much farther away. And that's Cepheid variable stars. I love Cepheid variable stars. I love Henrietta Leavitt. She was one of the main people that Edwin Hubble cited in his research that really broke all of this open. Unfortunately, Henrietta Leavitt, she had passed away right before the papers that were being used to really put this debate to rest came out. So it's posthumously that we're recognizing her. Well, Hubble also died, but anyway. The Cepheid variable stars are the rung that's immediately below what we're observing right now, which is the type 1a supernova. So just after we figured out how Cepheid variable stars are so useful for determining distances, we also determined that this very specific type of supernova is also a really good standard candle, that we know exactly how bright it's going to get, and so we can get a very accurate distance to it.
Thank you so much, Emily. And yes, I've put a link in the chat for further reading on Cepheid variable stars as standard candles. Okay.
Okay, we're there, Denise. Starting observation should be.
Oh, this is exciting.
This is 1 hour, 16 minutes.
Okay.
So we're there, we got it.
Okay, so this looks very different than screens you showed us before.
Yeah. Let me walk through everything that you guys just saw. So again, this is the GNIRS spectrograph, imager and spectrograph. We're using it in its cross-dispersed mode currently. So what cross-dispersed means is that we have a grating that's dispersing the light in the Y direction here. And then we also have a prism, a cross-dispersed prism, that's dispersing the light along the x-axis. So we get the entire near-infrared wavelengths that are accessible from the ground all in one observation. So all the way from 1 micron, which is well read of where humans can see, to about 2.45 microns, which is where the atmosphere basically cuts off the signal. GNIRS can actually observe even further red. There's two bands called the L and M band, which are at 3.4 and about 4.5 microns. It's much harder there. There's a lot more thermal emission from the atmosphere. So for this observation, we're just sticking to the part of the atmosphere that's relatively clean from thermal emission. So we're able to see a little bit fainter objects. And so we're dispersing the light and collecting all the information of the emission of this source, so the brightness of this source, at different wavelengths, all the way from 1 micron to 2.5 microns. And so as soon as we take our first spectrum, so that'll be about 5 minutes from now, maybe we can end it on that, Shamika. So we'll take our first spectrum. It's going to display in this thing right here. So this is a real-time analysis tool that allows us to see the data as it comes in, and then one of my jobs is to assess that data. So are we getting what we think we should be getting, given the conditions, given the target brightness, given kind of what is expected to be seen from this target, if there's some sort of expectations. Is there any contamination from, let's say, a satellite or something else? And so I'll watch this the whole entire night to make sure every time we have a new image that comes out, let's make sure that we got what we think we should be getting. If we don't, then I may change the observation that we're taking. I may increase the exposure time. We may move to another program entirely. But it seems like actually a relatively stable night, at least in terms of the clouds right now. And this observation can take effectively any amount of turbulence, so any amount of twinkling is okay for this particular observation. So I think we'll probably stick on this, and we're gonna keep taking spectra for about an hour and 15 minutes. So what I just did was to get us what's called acquired on this target. And this is, again, the same idea as I said before with MAROON-X, is we're trying to get all the light possible. We're trying to eke out every single photon that we squeeze out, every single photon that we can get from this source. So this is the slit. And there's a couple of reasons why you would want to have a slit for this observation. The slit sets the resolution element. So how finely you can break up the light when you create a rainbow. And so the narrower the slit, the more finely you can break up the constituent light, but the less light you get because you're narrowing the slit. And so it decreases the amount of light from the source. And so usually you want to compromise between, blocking out as little light as possible while still keeping the resolution that you want. Luckily for David, type 1a supernovae, very energetic events, they usually have very broad emission lines. And so you don't actually need a high level of resolution. So David used one of I think actually our largest slit for GNIRS, which is 1 arc second. And 1 arc second is a very small angular measure. But for astronomy purposes, it's actually quite large. And so he doesn't have a whole lot of resolution in this observation, but he will get a lot of light. And this is why he can accept observations that have a lot of twinkling, because even if the star, well, in this case, the supernova remnant is blurred out, he can still, his light bucket is large enough to deal with that to some level. And so when we took so I'll go back. So we first started with this image of the slit. So we just basically illuminated the slit on the sky. We took an observation in a band that, so a wavelength of light where there's thermal emission, some level of thermal emission from the atmosphere. And so if we just point at some random place in the sky, this is we're not shining a flashlight. That wouldn't work because it's near infrared light, but we're not shining a near infrared flashlight. The atmosphere is doing that for us. And so we're just integrating for a little bit, meaning we're just taking like a 3-second exposure, and there we see our slit illuminated. And so now we know where the slit is in our optical path. And then now here's a keyhole image. So GNIRS has the imager is a keyhole for reasons that are very complicated, but this is our field of view. So this is the full field of view. It's not with a slit in, it's just what GNIRS sees when it takes an image. And so as you saw earlier, this is this blurry little thing here is the supernova. This guy right here. And it may not look like much, and it also looks like there's a bunch of pattern noise here. But when I do, so this tool right here is something that Charlie Figura, who's a science operations specialist at Gemini North, and who's been featured in many Shadow of the Scientist sessions, he's helped to create. So he has this nifty little feature here where you can set a subtraction frame. This is really important in near infrared. So you take one image at one location, you take another image at a slightly different location, and you subtract the two. And the reason why you want to subtract is because the sky is so bright relative to the source that you need it to pop out. And so you're basically removing the sky to some level, but you still have fluctuations from the sky, but you remove the kind of white noise level from the sky. So you remove the brightness of the sky, as long as you do this fast enough, because the near infrared sky changes brightness on an absolute and relative level every couple minutes or so. I mean, it's constantly changing, but you can measure it on 30-second to 2-minute timescales. And so if you take these back to back, and these were taken very close to one another temporally, so maybe 45 seconds apart, you can really see the source pop out here. So we have a negative image, and that's where the source used to be. And then the positive image is where the source is now. So if I go back to I turn off the subtraction and I go back to the previous frame, you can see the source move like that. So it's blurry and faint here, but then when you do the subtraction through the magic of subtraction, magic of math, it pops out. And so then I know where the source is relative to where the slit was. And so I make another movement. Actually, I asked Denise to make a movement. So we make a measurement and we say, we know the slit is here. We know our source is here, and we want to pull that. Well, we want to move the telescope so the source appears here. We're not moving any galaxies or stars tonight, I don't think. And so we put we move the telescope such that the supernova is right centered on the slit. And I take another image through the slit. Okay, and so now this is our image through the slit. And so we have I've taken two different images, one where it's moved a little bit along the major axis of the slit, so in the X direction, this way, horizontal, and then one where it's centered right in the middle of the slit. And so this is the negative image, this is where it used to be, this is where the source is. You can see it's, it's hard to see actually, but we're getting light to the slit anyway. So this is the slit here. It's subtracted off, so it's kind of hard to see, but running from so basically where this orange box is, that's where our slit is. And so you can see the source is right centered in the slit. And so then at that point, we remove this mirror that's in GNIRS that's that's allowing us to take these pictures. We take that mirror out of the optical path. So that means it's no longer interacting with the light. And that allows the light to pass through what we call the dispersive elements. So the things that create the rainbow. And so this is the grating, this is the prism. And so we just took our first spectrum. Oh, what are we gonna see? Let's see.
I want to see a spectrum.
Oh my gosh. There it is.
Whoa!
This is the meat and potatoes of the scientific research in astronomy. It's like, how do you put light underneath the microscope?
Yep. So that's actually, this is a really strong detection of this source. So David's getting a lot of photons from this source. See if I can stretch it a little bit better. Yeah, so this is his supernova that he wants to look at. So this is a trace. This is basically a rainbow, and there's no colors here. So this is just a display. This is basically black and white. It's just telling us X number of we measured X number of photons at this location, or electrons as a result of photons interacting with our detector. And so you can see over on the left-hand side here, there's all these values, this thing right here. And this tells us like what's the intensity of light at that particular location. And these near vertical stripes, this is the rainbow of so this is a supernova rainbow. Not bad.
Yeah, so the where the light is brighter and then dimmer can also be used to indicate what types of elements are inside the gas of the supernova. So it's if you don't know what you're looking at, you might just like pass over the image, but through this image, we are able to calculate the composition of a star explosion in another galaxy.
Yeah, that's exactly what David's trying to look at. So actually, it's not common that type 1a supernovae have near infrared data, and there's all sorts of cool emission lines from elements in the near infrared. And so a lot of times, as I mentioned, the targets of opportunity, they take optical imaging or spectra. And so there are very wonderful atomic and mostly atomic transitions in the optical, but you get some very different species of emission from different elements in the near infrared. And as I mentioned earlier, you have this huge baseline of light with this observation. So over here on the right-hand side, this is roughly 1 micron here. Sorry, on this right-hand side, this is roughly 1 micron. This is all the way to 2.5 microns. So the range of human seeing is about 0.4 microns, something like that. And so this is, so this is 6 times-ish the range of human seeing, but in the near infrared. So it's a lot of light all at once. And David's looking for transitions of like nickel, of carbon that wasn't burned by the parent star, and trying to determine what that means in terms of the evolution of like what type of source gave rise to what happened before the supernova occurred. Did the star burn all of its material? Did it somehow have a runaway like puffing out explosive event? Was there what type of stellar remnant was left over? What was the composition of that white dwarf? So on and so forth. And so through the emission at certain wavelengths, we'll be able to tell the chemical composition of the it's called the ejecta, so the supernova ejecta. And I'll do one last thing before we call it a night, which is that so it's not only images that you can subtract, but it's also spectra that you can subtract. And so what we do is we do what's called slit knotting, and Ekta is very familiar with this. We do this all the time on MOSFire on Keck, and you just up, down, up, down, up, down, up, down. So you're just, the source is, so in this case, the supernova is falling at 2 different locations on your detector. It's usually this, what's called an ABBA pattern. So you go A position, then you move the telescope just a little tiny bit along the major axis of the slit, so along the X dimension, and the supernova shows up at a different location. And so we can actually subtract the 2 spectra. So let's do that right now, because it's tough to see the spectrum here with all these super, super bright lines. And these bright lines are not from the supernova. These bright lines are from the Earth. And in this case, Earth is nice, it's a wonderful place, but we don't like the emission from the atmosphere.
How is that atmosphere?
Yeah, it's pretty fine. So let me set it. And then, so it went away because it just subtracted itself from itself. But then I'll go to this one. Okay, there we go.
Wow.
So this is the first spectrum that we took. So if I turn this off and I go, right. So you can actually see when I blink between these 2 frames that this vertical structure here is actually moving. It's the telescope that's moving, not the supernova itself. And so 2 different locations on the detector. And then when we do the subtraction, we see this negative trace from where it was before and the positive trace from where it is now. And so we've removed, you can still see that there's some residual from this what we call air glow lines or sky lines from the atmosphere. As I mentioned, yeah, the atmosphere, the brightness, relative level, and the absolute level changes on like 30-second to 2-minute timescales. These 2 observations were taken 5 minutes apart, so it's not designed to really subtract off the atmosphere super well. But that's okay for David's observations because the atmospheric lines are fairly narrow, and the lines that he is looking at from the supernova are usually very broad. So like for the science that Ekta and I do, the lines that we look at are very narrow in general, and they're about maybe twice the size of in terms of wavelength of these sky emission features. And so when Ekta and I design observations, we make sure that we take them in fairly rapid succession. We do about every 2 minutes or 3 minutes so that we can really get the skylines removed as much as possible. And so, yeah, so this is not the final data product that David will use, but it's, you know, some close approximation of that. And so he would really just then grab all the light from this location in the slit. This is all the same source. It's just different wavelengths. So all the supernova. And he would plot it. So the intensity versus the wavelength. And then what he would see is certain wavelengths have big emission features. And he'd say, aha, because I know from lab experiments that some other person did that one there, because I know the distance to the source and I know in a lab what the emission of, I don't know, nickel 6 is. So quintuply ionized nickel. I know what that is. And I know that this source is this far away, and so the light should be shifted from the expansion of the universe by this much. And so, aha, that's nickel 6, and I can measure the intensity, and then that tells me that there's, you know, I do some complicated math, and I say, aha, that means there's, I don't know, 0.1 solar masses of nickel in that ejecta, and that tells me something about what happened, you know, to the explosion itself. It's a lot of nickel. There's a lot of nickel in
A lot of nickel.
Be a rich person if you were able to get that in.
Rich person and nickels. That's the way.
Nickels.
This is a fabulous point to wrap up our session, Brian. So with these kinds of target of opportunity observations, how quick do those who requested these observations, how fast did they get it? And then when could we maybe read about what David and his colleagues find from this data?
Yeah, honestly, so I was actually text messaging with David right before the session to ask permission to do this. And he was mentioning that his graduate student that's working with him, Willem Hogdam, I don't know if I'm pronouncing the last name correctly, but Willem is writing a paper exactly on these data. And so this is, you know, what we do in science. We get the data, we analyze the data, then we write a paper, we say, I have 0.1 solar masses of nickel, and that means blah, blah, blah for, you know, whatever, that white dwarf, and this is the consequences. You know, if I look at enough of these, I start to see a pattern, and I say, yes, okay, so that's probably what happened to this set of stars, and this is why, and then people can go back and refine models of stars, of supernova explosions, and then you take more observations, and that's the kind of life cycle of how science moves forward, at least in astronomy and in most sciences, honestly. And so Willem will write this paper and he'll say, yep, got this data, here's a bunch of nickel, hooray. But he'll do some serious analysis, and he'll reduce the data, meaning he'll be very careful about making sure to extract the data properly and take care of the noise properties and everything. But he gets this data in 20 seconds. So David could be out at a bar. Let's say theoretically, he's out at a bar drinking right now. Who knows? No one knows. But let's say theoretically he's at a bar drinking right now. He would get an alert basically on his phone that says, hey, we just slew to your target and we took an observation. And he could then call Willem and he could say, hey, Willem, just got this, observation of the supernova. And Willem says, okay. And then he, grabs the data off our archive and then he downloads it. We have very good software that allows people to reduce their data so that it's scientifically ready. And then he says, aha, okay, I've analyzed it and I see this and I can start writing a paper on it. And this is for people that work on transient science, so supernovae. Usually it's done pretty quick. So like Ekta and I have a program on Gemini South right now, and we got some observations, and we're just kind of relaxing. We're gonna reduce the data over time, but we're not worried that somebody else is going to take our data or that they're looking at the same exact thing. So we don't work on transient science, and so I admire the people that do because they go from triggering to downloading the data to reducing the data to analyzing the data to paper could be as fast as like a couple days, honestly.
So keep in mind the observatory doesn't sleep. We're set to be taking observations on Christmas, New Year's sort of thing. So very realistically, in just a few days, somebody could be at a bar getting ready to celebrate New Year's, and they'll get a text message that their data has come in. It's time for them to start the new year by jumping onto a paper.
Yep. Yeah. So yeah. I mean, usually for these types of things, there's telescopes all over the world that are monitoring. And so it's really, I mean, people that do transient science, I don't know how they ever sleep on that, honestly, because they'll get an alert that says, oh, this thing is exploding. And then they're like, oh, I gotta go trigger on Gemini. And then we're, then they take a nap and 2 hours later, we're like, we're on your target. They're like, ah. So it's not the type of science that I would want to do. We're slow and steady. Ekta and I are slow and steady.
I love it. I love it. Well, this is fascinating. What a wonderful session. And to be able to be a part of this target of opportunity experience here tonight was very, very special. Thank you so much, David, for allowing us to be a part of your TOO experience, and to your grad student, Willem. Thank you so much for that. And to every one of our science hosts tonight, Ekta Shah, Emily Peavy, Denise Hung, Brian Lameau, thank you so much for allowing us to shadow you for this session. And Brian, I believe we'll have a session, another Gemini session coming up next month in January.
Yeah, I think we have 2 actually. One is for new users of Gemini, so that'll be mostly people it'll be almost exclusively for people that have proposed successfully to Gemini, either North or South. And then we're gonna have our first ever, if everything goes well, our first ever Gemini South Shadow the Scientists on, what is it, the 9th of January.
Oh wow, that is coming up soon.
Yeah. So that's still in the works, but it'll be Zachary Hartman will be joining us, who's led many Shadow the Scientist sessions with Gemini North. Zach is now a postdoc at NASA Ames in the Bay Area, California. And he will be helping to lead a session on the Zorro instrument, which is a speckle imager in Gemini South, along with other people from the NASA speckle team. So that's super exciting. Looking forward to it, and that's open to the public, so anybody's welcome to join. And I think we'll put out the registration link maybe in the next couple days or so.
Yes, absolutely. Yes, looking forward to that. Thank you all so much for joining us for this session, and to all of you in the control room and Ekta from India. We are grateful for your time and expertise. Until next time, aloha.
Mahalo.
Aloha. Thanks, Ekta.
Thank you, and thank you, Jamika.